and welcome back for some more structural engineering. Today we'll be solving more reactions, specifically reactions in a cranked beam with some point loads. The cranked beam will help us understand how the forces in different directions and with different distances influence the reaction forces. So let's get to it. The exercise we're going to solve today is this beam with a crank. Let's give some labels here, so let's call this A, B, C and D. This is a parametric example, as we can see. We don't know the real lengths. We've got A and 0.25A given on the beam. We've got a 0.1A. So all the distances are parametric. A could be anything. It could be 2 meters. It could be 10 meters. Also in terms of the forces, we've got 0.5P. We don't know what the actual value of the kilonewtons is, so we don't know if it's 10 kilonewtons, 20 kilonewtons, because P could be anything. But parametric examples are really important to get your head around, because once you can solve something parametrically, then you can solve that case for any number that could come your way. So let's see how it's done. To solve this, the first thing we need to figure out is what type of supports we have and replace them with forces. That way we get our free body diagram. So we can see that at point A, we've got a pin support. That means two reactions, two perpendicular reactions. Let's just delete this support and replace with two forces, AY and AX. At D, we can see that it's a roller support. So that means one force perpendicular to that line of the roller support, which means that we've got one force dy here. And now we have our free body diagram. Once we have the free body diagram, we can solve the reactions. Let's start off by looking at sum of forces in the x direction equals 0, with this being my positive direction. So here I've got AX and I've got this 0.5p in the opposite direction, so that is minus 0.5p equals 0. And that means that AX equals 0.5p. So as we mentioned before, we don't really know what the exact value is, but we do know that AX is a reaction and we've gotten it in units of force. Let's have a look now at solving the sum of forces in the y direction, with this being my positive direction. So in y, I can see that I've got AY, and then if I'm going kind of from A to D, I've got minus 0.5p. The 0.5p at B is not in the y direction, so that doesn't contribute. But then between C and D, I've got a plus 0.5p. And then at D, I've got dy, which is also going up, so plus dy equals 0. I can see that this 0.5p and this 0.5p cancel each other out. They add up to 0. And so I'm left with AY plus dy equals 0, or ay equals minus dy. And that's all I know for now. So I don't know what the values are, but I do know that they're going to be equal in value, but opposite in direction. And the last thing that I want to do is sum of moments. I can do it around A or D. I'm just going to choose A in this instance, because there are two forces passing through. And also, if I look at this 0.5p here, and I look at its line of action going along this way, I can see that it also passes through A. So by doing moments around A, I don't have to take into account AX, AY, and that horizontal 0.5p. So what I do have contributing to moment is this 0.5p. It contributes a negative moment, so minus 0.5p. And this is because, as we've mentioned before, this is its line of action and it needs to rotate around A, which means it'll have to go back this direction, which introduces a clockwise moment, which in our sign convention is negative. Now that needs to be multiplied by the distance. It's always the perpendicular distance. So I can see here that that distance is going to be from the line of action of the force to A is this distance here. So that is going to be times 0.25a. Moving on to the next thing that contributes to moment, I've got this 0.5p. It contributes a positive moment, and I can see that because if I do the same thing, so continue along the line of axis and then go back to rotate around A, I can see that it contributes in a counterclockwise direction, meaning according to our sign convention, that it is a positive moment. So plus 0.5p, that's the force, and then times a distance, which is this distance here, the perpendicular distance to the line of action to the point of rotation. And that is 0.75a. And then the last thing I've got contributing to moment is this dy here, and that contributes a positive moment as well. So plus dy, and the distance here is the whole distance. So all of a times a, and that needs to equal 0. So you can see here in green they're the forces. Each force is multiplied by a distance, which is in purple. Let's sum this all up. If I sum it up, I get that 0.25pa plus dy times a equals 0. I can divide by a, and I will get that dy equals minus 0.25p. And now if I go back to this equation, ay equals minus dy, which is minus 0.25p, which is plus 0.25p. And that's all the reactions solved. Let's put them back into our structure, and then let's do a check. Let's replace everything. Instead of ax, I've got 0.5p. And that also means that the direction that I assumed in this case was correct. Instead of ay, I've got plus 0.25p. Once again, direction assumed is correct. And dy turned out to be minus, which means that I assumed incorrectly, and instead of pointing upwards, it is pointing downwards, and it is 0.25p. Let's check this in two ways. So the first thing that I can do is I can do sum of moments around B. This would be the typical way that we check things. So let's do that as a first check. Sum of moments around D equals 0. So sum of moments around the other reaction that we didn't consider last time. So in order to do that, everything here is contributing to the moment apart from the 0.25p reaction at D. Let us start off from A to D. I'm going to start off with this first reaction force here of 0.5p. We can see that it contributes a negative reaction, so minus 0.5p, and the distance is going to be the perpendicular distance to the line of action. So if this is the line of action, the perpendicular distance to D is this distance here. So times, just like before, I'll do the distances in a different colour, 0.1a. The next thing that I'm going to consider is this force here. It also gives a negative moment, so minus 0.25p. And the distance in this case is the whole distance because it's the perpendicular distance from the line of action to D, and that works out as A. The next thing we have is this 0.5. It gives a positive moment, so plus 0.5p times the distance that is perpendicular to the line of action until D, which is 0.75a. Then we've got another positive moment, this time from this force here at B. So I'm just continuing on this next line, so plus 0.5p, and we can see that the distance here is 0.1a, and the last force to contribute a moment is this force here. This time we've got a negative moment, so minus 0.5p times a distance of 0.25a. And if we have done all of our calculations correctly, this should be in equilibrium, so this should equal 0. Let's check. So minus 0.05pa minus 0.25pa plus 0.375pa plus 0.05pa and minus 0.125pa. Let's add all of these up. And if you do that, that indeed equals 0. So we can say the check is complete and we've calculated the reactions correctly. But there is another way I want to show you, and that links to what we discussed before on coupled loads. If I look closely, I can see that these two forces, this one and this one, are a coupled force. That is, they are equal in magnitude but opposite in direction, parallel to each other. That means that they always contribute the same moment no matter where we are in the structure. Let's calculate what that moment is. So moment from couple 1. It's going to be a positive moment, right? Because we can see that it is going to turn. It's going to go up that way, and down that way, and then back up that way. So we can see that this is a counterclockwise moment, which is a positive moment. So first things first, it's a positive moment. And the moment itself is always going to be the value of the force times the distance between the forces. So it's going to be plus 0.5p times, you can see the force, the distance is this distance, times 0.5a. So that gives me 0.25 pa. Now, if I were to use that knowledge and do my sum of moments around A before I'd solved the reactions, I would have had dy times A, as it were, and this moment. So plus 0.25 pa equals 0, and I would have found that dy equals minus 0.25p. I can also see that to balance this out, I've developed another coupled force, right? This, and they should create a moment as well. Let's see what the moment they create is. So this time it's a negative moment of 0.25p, that's the force, times a, and that gives me minus 0.25 pa. And what I can see is that these two moments from coupled force balance each other out. And that's just to demonstrate that sometimes it's important to see what is in the structure and how it works. So it's a good sense check as well. But we've validated that the reactions that we've calculated are indeed correct. And that's it. We've seen how to solve reaction forces when we have a crank in our beam, meaning that forces in different directions can influence the reactions at different points. I hope that's been helpful, and I hope to see you again for some more structural engineering. Bye for now.